Reflections and Symmetry. Y equals negative f of x is a reflection about the x-axis, and y equals f of negative x is a reflection about the y-axis. First of all, I'm going to make the graph. I'm going to label G as equaling to negative f of x. So what I'm about to graph is a reflection of f of x about the x-axis. So each point is going to be on the other side of the x-axis of same distance away. So my first point will become then the negative 3 positive 1. This point, when I reflect it, becomes, that should be negative 1 for the y. For the x will stay negative 1, but the y value will flip from positive 1 to negative 1. And I'll connect my line segment. 3, 1, what I'm going to do to reflect it about the x-axis is change that to a negative 3. I'm sorry, a positive 3, but a negative 1 for the y value. So the only thing that changed was the y value. Same thing here. The x value stays the same. The y value becomes a positive 1. So that is the graph of negative f of x. Now, another reflection would be the reflection h of x, which I will allow to equal f of negative x. In this case, I'm reflecting everything over the y-axis. To avoid any confusion, I'm going to start by making a new graph of f of x. It's the same original graph. And now I'm going to graph h of x. All I'm doing is keeping the same y value for a negative value of x. So the x value changes, and I'm going to end up with a point 3, negative 1. This point, negative 1, positive 1, the x value is going to change, and I'll end up with a positive 1, and the y value stays the same. So this line segment now has been reflected over here. Now to complete the top one, I'm going to reflect the point 3, 1, and it will end up being the point negative 3, positive 1, or right here. And I will connect it. And last but not least, 5, negative 1 becomes negative 5, negative 1, or about here, and I connect my pieces. So what I have done is flip the sign of every x value and kept the y value the same. This is a reflection about the y-axis. We're now going to explore the connection between even functions and a reflection about the y-axis. Notice, a function is called even if for every x value f of x equals f of negative x. Meaning, if I take a look at the graph, I'm going to give a couple graphical examples. This graph here is an example of an even function. If you notice, the graph is a reflection of itself about the y-axis. Meaning, any point I choose on this graph will have an identical point if I go straight horizontally, the same distance over, I'll have a matching point on the graph itself. Another example of an even function would be maybe this graph here. And again, what we notice is the right-hand side and the left-hand side are reflections of each other about the y-axis. Now, if you're given a formula, for instance, f of x equals x squared minus 8, and we'd like to test this formula directly to see if it is even or not, what I'll start by doing is plugging in negative x into the formula everywhere I see an x. Next step is to simplify. Notice my parentheses with the negative x on the inside of the parentheses. Now when I simplify this, negative x times negative x is positive x squared minus 8. Notice these two formulas, f of x and f of negative x, are identical for all x values. So we would say the original formula is an even function. Another example, what you do not want to confuse is because a function has an even exponent doesn't necessarily make it an even function. For instance, here is another parabola. However, if I was to test this parabola to see if it was even or not, by plugging in negative x everywhere I see an x, notice in parentheses I replace x with negative x. Now, when I simplify this formula, negative x times negative x is positive x squared, but I have a plus negative x, or simply minus x. These are not the same. Because they are not the same, f of x is not even. We've talked about even functions. Now we're going to examine odd functions. A definition of an odd function is f of x is odd if f of negative x equals negative f of x for all x values. Another way of saying that is if I do a vertical reflection, it will be the same location as the horizontal reflection onto itself. An example of this. In this case, if I look at this graph, what we have here can be viewed as either if I reflect this across the y-axis and this across the x-axis, my graph will end up at the same location. That's one way of looking at it. Another way, if you want to move this negative over, is to say if I do both a reflection around the y-axis and then a reflection around the x-axis, that I'll end up in the same location. So if I was to take this part of the graph here and first reflect it across the y-axis, and then I was to take that reflection right there and reflect it around the x-axis, I would end up reflecting the graph onto itself. Another way of viewing this is a point reflection. This graph is reflected through the origin onto itself. So let's take a look at a couple of graphs. take a look at this graph here as f of x. This would be an example of an odd function. If I view it as a point reflection, that basically means if I take any point on this graph and I go through the origin and I go the same distance to the other side, the graph will be on itself. So that's basically doing both a vertical and a horizontal reflection is the same as going through the origin as a point reflection. Again, this point, if I go through the origin and I go the same distance on the other side, I'm still on the graph itself. Now let's examine this looking at it as a formula. You'll notice using this way of writing it, I start off with the same procedure as I would to find out whether the function is odd. I'm going to calculate f of negative x. So let's give ourselves a formula. And I'm going to determine if this function is even or odd or neither. So I'll start off by calculating f of negative x. So I plug in the negative x. Everywhere I see an x, notice I'm using parentheses and the negative x is going inside. Now I'm going to simplify this. Negative x times negative x is positive x times negative x is negative x cubed. And now I'm subtracting a negative x, which is the same as adding x. To test if they're even, these two functions must look identical. They are not the same. Since they're not the same, I can say f of x is not even. Next thing I'm going to do is calculate negative f of x. What do I mean by calculate negative f of x? Another way of interpreting what is written down here is change the signs of everything on f of x. So here's f of x, and I'm going to change the sign of everything. So I'm just going to put a negative through everything. So x cubed becomes negative x cubed. Negative x becomes positive x. And the question, let's go back to the original statement for odd functions. If f of negative x equals negative f of x. Well, let's check out what I have down here. Here's f of negative x, which simplifies to this, and here is negative f of x, which simplifies to this. Because these are the same, I can say f of x is odd, or an odd function. Okay, we have looked at even functions which have symmetry around the y-axis. We've looked at odd functions which have symmetry around the origins, and we've looked at those for both graphs and equations. Now we're going to look at a table. How do I evaluate symmetry around a table? First thing is I need to go ahead and extend my table. I need another column. In this case, I'm going to look at f of negative x. So it's a little weird how we're going to do it, but when I plug in negative 3 into here, I need to change it to positive 3. So basically, this is going to have the same output for the opposite sign of x. So I need the output not for here, but the output for here, which is 6. I need, for this line, I need the output not at -2, but at +2, which is 1. Here I need the output not at -1, but at +1, which is -2. I can't change the sign of 0. Here I need the output at -1, which is -2. I need the output at -2, which is 1. And I need the output for x -3, which is 6. So this is how I complete my table by not looking for this output, but for the output at the opposite sign of x. Now, notice my table is the same y values whether I look at a negative value of x or a positive value of x. Both have the same output. That means this function is definitely even. Okay, now I'm going to look at another table. So a function is even if I plug in a value for x and get an output, and if I change that sign, I get the same output. Well, here I did not get the same output. So when I changed the sign of x, I ended up with different y values. This is not even. What about the possibility of odd? There was two ways I could express odd functions. One definition for odd function was if f of -x equals -f of x. I also said I could move that negative sign to the other side and evaluate it from this direction. Let's see what happens here. If I change the sign of x, it should result in a different sign of y, but the same y value with different signs. So let's examine that and see if it works. If I change the sign of x, I should end up with the same y value, but one has a different sign than the other. That seems to work for my first pair of x points. Let's look at the next pair. Same thing must be true. If I change the sign of the x's, I must have the same y with different signs. It works. Same x but with different signs gives me the same y with different signs. If that works for every possible x value, then we can say f of x is an odd function.